Red dust settled around the legs of the Viking 1 lander. The year was 1976, and the silence of the Martian desert was absolute. A radio signal traveled across the void, a thin thread of light connecting two worlds separated by millions of kilometers. Engineers waited for the first ping of data to return from the rusted surface. The objective was total precision. The solar system was a clockwork mechanism governed by the laws of Isaac Newton and Albert Einstein. Every planet followed a path written in mathematics. Error was not an option in a universe defined by celestial mechanics, yet a strange pattern emerged from the digital noise. Mars was not where the calculations said the planet should be. The red world was drifting into the dark. This anomaly is more than a navigation error. The missing meters represent a ghost in the gears of the cosmos. This story describes the fundamental scale of the cosmic home that humanity occupies. The astronomical unit serves as the primary yardstick of the universe. If this yardstick changes, the foundation of every star and galaxy shifts alongside the measurement. The data from Mars revealed a truth that contradicts centuries of theory, a gap in the heavens, first measured by researchers like George Krasinsky and Miles Standish. The solar system is expanding. Every century, the distance between the Earth and the Sun grows by 15 meters. The drift is small, a mere whisper in the dark, but the expansion defies the known laws of physics. The clockwork is breaking. The planetary family is slowly drifting apart. The official narrative suggests that the solar system is a stable and eternal arrangement. Standard models of gravity predict that the sun should pull the planets closer as solar mass radiates into the void. Instead, the planets are pushing away from the center. This investigation explores the missing meters of the cosmos that the textbooks cannot explain. Fragments of evidence range from the strange behavior of the moon to the unexplained speed of probes exiting the system. The official story is incomplete, and the missing data points to a revolution in understanding. Over the course of this journey, the investigation will descend through layers of celestial mechanics and hidden physics. The path begins with the radar-ranging pioneers who first measured the void between worlds. We will dismantle the anomalous orbital motion of the moon, an orbit that changes shape in ways that tidal friction cannot explain. The investigation follows the Pioneer spacecraft into the dark, where probes experienced a mysterious sunward tug at the edge of the system. We will hunt for the edge where General Relativity fails to account for the energy games of spacecraft during Earth flybys. Finally, we will confront the theories of dark matter accretion and modified gravity that attempt to solve the puzzle of the expanding astronomical unit. We will discover that the solar system is not a static clock, but a changing organism. The question is whether our mastery of gravity is merely a local approximation of a much deeper reality. The 15-meter error signals that the universe remains a stranger to human mathematics. By the end of this journey, the solar system will no longer feel like a stable home, but a shifting frontier where we are mere passengers on a drifting world. The truth lies in the missing meters of the very yardstick we use to define the cosmos. Our investigation begins now. If this kind of deep exploration resonates with you, if you value understanding over easy answers, consider subscribing. And if you are able, donating helps us keep making these long-form investigations. Either way, thank you for being curious. That signal from the red dust of Mars was only the first chapter. While the Viking landers gave us the hard evidence of the drift in 1976, the true history of the missing meters stretches back centuries. The Viking landers represented the pinnacle of 20th century engineering. For the Viking landers to find a discrepancy, researchers first needed a standard, a baseline. For most of human history, that baseline did not exist. The solar system was a chaotic shifting of lights in the sky, unmeasured and terrifyingly vast. To understand why a 15-meter error matters, the investigation must first examine the sheer arrogance of trying to measure the void. The mystery begins with a young English prodigy named Jeremiah Horrocks. The year was 1639. Horrocks was just 20 years old, remarkably working as a poor curate in the tiny rain-swept village of Muchhool. The village of Muchhool was a remote outpost of mud and thatch, a place where the wind howled through the gaps in the timber frames of the small church. The life of a 17th-century curate was one of quiet poverty, deep reflection, and presumably a very high tolerance for cold porridge. While the rest of Europe was fighting the 30 Years' War, a conflict of unprecedented violence and religious upheaval, Horrocks was fighting a different kind of battle. The young researcher was fighting the planetary tables of Johannes Kepler. The father of celestial mechanics had predicted that Venus would pass close to the sun, but miss the solar disk entirely. But Horrocks ran the math again. The curate sat by candlelight, scratching out orbital elements with a quill, checking the inclination, checking the nodes. Horrocks found a mistake, a tiny error in the tables of Johannes Kepler. When the researcher corrected the math, the result was terrifying. Venus was not going to miss the sun. A transit was imminent. Tracking a transit in the 17th century was a feat of extreme patience. The alignment of Venus and the sun is a rare celestial geometry, occurring in a pattern that skips over a century at a time. Horrocks knew that if the math failed, the opportunity would not return for another 8 years, and after that, not for another lifetime. Muchhool was far from the academic centers of London or Oxford. Horrocks relied on a small telescope, a simple arrangement of glass and wood that the young man had purchased with meager savings. The equipment was primitive by modern standards, and the purchase likely left the curate unable to afford even the most basic 17th century luxuries, like a better pair of shoes or a less drafty bedroom. The glass was prone to bubbles and streaks, making every observation a struggle against the limitations of the material. Horrocks spent endless hours grinding lenses with fine sand, seeking a clarity that remained just out of reach. The glass lenses were imperfect, often casting distorted halos around every star. Yet, the mind of the curate was precise. The researcher spent weeks calibrating the instrument, adjusting the focal length by the light of a single tallow candle. The dedication of the young man was a demonstration of the human desire to map the heavens. On a cold Sunday in November, Horrocks set up a simple telescope in a darkened bedroom. The young man did not look through the lens because the light would have blinded the observer. Instead, Horrocks projected the image of the sun onto a piece of white card. The card was exactly 6 inches in diameter, marked with a grid to measure the position of the planet. Imagine the scene: a cold, drafty room, the smell of dust and old wood, the faint light of a winter sun filtering through the lenses, and the silence. Horrocks waited. The church bells rang. The curate had to leave to conduct the service for the village. Horrocks must have felt the terror that the clouds would roll in and steal the moment. The English weather is not known for cooperation, but when the researcher returned to the room in the afternoon, the clouds parted. There the dot was, a tiny black dot, perfectly round, crawling across the face of the sun. This sight was more than an absolute shadow. The dot represented geometry in motion. The sight was the clockwork of the universe, revealing the inner gears. By timing exactly how long the transit took and measuring the angular size of that black dot, Horrocks could use the principle of triangulation to measure the distance to the sun. Triangulation involves measuring the angles to a distant object from 2 different points and using those angles to calculate the distance. The curate was doing trigonometry with the cosmos. The number Horrocks calculated was 95 million kilometers. Now, a critic might say the real number is 150 million. Horrocks was off by 30%, but that observation misses the point. Before the work of Horrocks, the best minds in astronomy thought the sun was just a few million miles away. Ancient thinkers thought the planets were cozy neighbors. Horrocks blew the roof off the entire solar system. The young man realized that the planets were not close. The worlds were drifting in a massive, truly crushing void. Horrocks was the first human to feel the true scale of the planetary system. The curate looked at the paper and realized that humanity was effectively nothing. Fast forward 300 years, the Cold War turned the sky into a battlefield. The invention of radar changed everything. In the 1960s, a team led by Erwin Shapiro at Lincoln Laboratory began doing something that Horrocks could only dream of. The researchers stopped looking at the planets. The team started screaming at the worlds. The scientists built massive klystron tubes at the Millstone Hill Observatory. These vacuum tubes were the size of a person and could generate 400 kilowatts of microwave power. To prevent the tubes from melting under the intense heat of the electron beam, engineers had to pump hundreds of gallons of chilled water through the cooling jackets every minute. The power draw was so massive that the researchers had to coordinate with the local utility companies to ensure the town did not go dark during a transmission. One can imagine the local residents wondering why the lights flickered every time a scientist wanted to yell at Venus. The researchers pointed giant dishes at Venus and Mercury and fired pulses of radiation into the dark. The method was no longer about geometry. The technique was about time. The team sent a pulse of microwave radiation screaming across the void at the speed of light. The researchers waited for minutes, listening to the static of the universe. The team waited for the pulse to hit the acid clouds of Venus, scatter, and bounce back. This process was far more difficult than bouncing a signal off a metal airplane. The planets are massive, but the planets are also far away. Most of the energy sent by the transmitter is lost to the inverse square law. By the time the signal hits Venus and returns to Earth, the pulse is 1 trillion times weaker than a cell phone signal. Detecting this return required a technique known as coherent integration. The scientists had to sample the incoming noise for hours, using the expected Doppler shift to narrow the search. The Doppler effect means the frequency of the radio waves shifts based on the velocity of the planet relative to the Earth. If the planet moves toward the Earth, the waves compress. If the planet moves away, the waves stretch. And then the scientists caught the echo, a whisper from the void. A signal so faint the pulse was buried in the background noise of the galaxy. But by integrating the signal over hours, the researchers could pull the ghost out of the machine. By measuring the time delay with atomic clocks, the team could measure the distance to the planets with an error margin of less than 1 kilometer. The scientists turned the solar system from a painting into a map. Now, a skeptic might think that a few kilometers of error is still sloppy. But remember, the researchers were measuring a gap of 40 million kilometers. That level of precision is equivalent to measuring the width of a human hair from across a football field. To appreciate the scale of this achievement, one must understand the precision of the deep space network. The signals travel at nearly 300,000 kilometers per second. Even a tiny error in the clock would translate to a massive error in the distance. The researchers used hydrogen maser clocks, devices that are so stable that the clocks only lose 1 second every 30 million years. The researchers expected to find a perfect match with the laws of general relativity. The math of Albert Einstein had predicted the precession of Mercury and the bending of starlight. Surely the orbits of the inner planets would follow the same predictable curve. The processing of this data occurred within the Solar System Data Center at the Jet Propulsion Laboratory. Engineers used sophisticated software known as the Orbit Determination Program to filter out every possible source of error. This program accounts for the rotational speed of the Earth, the atmospheric delay of the radio signals, and the relativistic time dilation experienced by the spacecraft. The researchers even accounted for the minuscule pressure exerted by the solar wind on the lander antennas. The objective was to create a perfectly clean dataset where only gravity remained. The team believed that once every known force was removed, the residual errors would disappear. But when a researcher measures something with that level of precision, the observer starts to see things that cause discomfort. Standard physics dictates that the solar system should be stable, or specifically, the system should be evolving in an incredibly predictable way. As the sun burns through the solar fuel, the star loses mass. The sun fuses 4 million tons of hydrogen into helium every single second. That mass is converted into energy. Light and heat radiate away. At the same time, the solar wind strips tons of charged particles from the surface and hurls the matter into space. The sun is getting lighter. Standard gravitational theory says that as the central mass decreases, the gravitational grip should weaken, the leash should get looser. However, the definition of the astronomical unit in relativistic celestial mechanics is complex. Paradoxically, the theoretical prediction, calculated by dynamicists like Elena Picheva and Miles Standish, is that the orbit of the Earth should shrink by about 0.3 centimeters per year due to the interplay of mass loss. Elena Picheva, working at the Institute of Applied Astronomy of the Russian Academy of Sciences, and Miles Standish at the Jet Propulsion Laboratory, are the titans of modern ephemerides. These researchers spend decades refining the mathematical models of planetary motion. The math is solid. The prediction is clear. Think of the system like a figure skater spinning on ice. As the skater pulls the arms in, the athlete spins faster. The conservation of angular momentum ties distance and velocity together. The solar system is a closed system. The system has rules. But the solar system is acting like a skater who pulls the arms in, yet somehow the body gets wider. The theory predicts a contraction of 1/3 of a centimeter. The radar data shows an expansion of 15 meters per century. That is 15 centimeters per year. The sign is wrong. The magnitude is wrong. The discrepancy is off by a factor of 50. This gap is more than a missing variable. The gap is a sign that the engine of the solar system has a gear that humanity cannot see. The investigation is comparing a theoretical contraction against an observed expansion. The gap between the theories, specifically that 15 meters per century, represents the astrometric anomaly. The drift implies that either the experts do not understand the sun, or the scientists do not understand gravity. Imagine you are an architect. You build a hallway that is exactly 10 meters long. You measure the hall with a laser rangefinder, 10 meters. Perfect. You come back the next day and measure the hallway again, 10 meters and 1 millimeter. You assume the shift is a temperature fluctuation. The concrete expanded. You come back a week later, 10 meters and 7 millimeters. You check the foundations. The stones are solid. You check the blueprints. The plans say the hallway should be shrinking because the building is settling into the bedrock. You measure the distance every day for a year. The hallway is definitely growing. The structure is stretching. The doors are moving further apart. the carpet is tearing, and you are standing in the middle of the hallway, wondering if the floor is moving, or if the laser is broken, or if the concept of length means something different today than the concept did yesterday. This unsettling realization is the feeling of existential dread that haunts modern astrometry. The community built a cathedral of physics on the assumption that the ground was solid. But the ground is moving. The re-evaluation of the yardstick changes the scale of the planetary home. If the astronomical unit is expanding, the local maps are stretching in ways that the experts cannot account for. This drift is not a universal expansion of space, but a local anomaly happening right here in the backyard of the Earth. If this expansion is real, the stakes are incredibly high. The astronomical unit is built into the fundamental constants of the ephemerides. These are the mathematical tables that tell the world where everything is located in the sky. If the astronomical unit is changing in a way that general relativity cannot explain, then general relativity is incomplete. This 15-meter error is a crack in the foundation of the Cathedral of Albert Einstein. The error suggests that on the scale of solar systems, gravity behaves differently than gravity does on the scale of black holes or the scale of apples falling from trees. Some physicists have tried to explain the drift away as a measurement error. These skeptics argue that the asteroid belt is perturbing the orbits or that the solar wind is pushing the spacecraft harder than expected. But the numbers do not line up. The asteroid belt is too light. The solar wind is too weak. Others have suggested wilder theories. Dark matter cores in the sun, the expansion of the universe itself leaking into the solar system, a modification of inertia. The implications ripple outward. If the experts cannot explain the motion of the Earth around the sun, the most studied relationship in the history of science, how can the scientific community trust the measurements of dark energy accelerating the distant galaxies? Humanity is building a model of the universe on a foundation that is shifting 15 meters every century. The precision that researchers worked so hard to achieve has revealed a fundamental flaw in the understanding of reality. But before the investigation tries to rewrite the laws of physics, we must look for other clues. The Viking landers were not the only witnesses to this cosmic crime. Another body exists in the solar system, much closer to home, that is also behaving badly. A body that humanity has visited, walked on, and covered with mirrors, the moon. To find the answer, the investigation must leave the red dust of Mars and look at the silver mirrors on the lunar surface. We must examine a 38-year record of laser pulses that reveal a discrepancy even stranger than the one found by Viking. The investigation moves from the expanding yardstick to the eccentric orbit of the moon. We must understand why the silver satellite of the Earth is pushing away from the cradle in a way that defies classical logic. This revelation is where the mystery deepens, and the closer the observer looks, the less the pieces fit. This concludes the first entire stage of our forensic analysis of the solar system. The investigation now turns from the red dust of Mars to the silver light of the moon. While the Viking landers revealed a 15-meter drift over the scale of decades, a far more intimate witness exists much closer to the Earth. Moon has been a companion for 4 billion years, locked in a gravitational embrace that defines the tides and the very length of the day. But the moon is not a static observer. This silver satellite is an active participant in a cosmic departure. To understand the missing meters, the investigation must look at the most precise dataset in the history of astronomy. This data did not come from a telescope or a probe flying past the planets. This data came from the surface of the moon itself, left behind by the men who walked there. On July 21st, 1969, Neil Armstrong and Buzz Aldrin deployed the first of several retroreflector arrays on the Sea of Tranquility. These devices are not complex electronic sensors. The arrays are simple blocks of high-purity silica glass, designed to act as perfect mirrors for light. Each corner cube prism is a masterpiece of geometric engineering. The design relies on the principle of total internal reflection. When a photon enters the front face of the prism, the particle strikes three mutually perpendicular surfaces in succession. Because these surfaces are oriented at exactly 90 degrees to one another, the light is reflected back in a direction that is perfectly parallel to the incoming path. This property is known as retroflexion. This property is the same principle found in the reflectors on a bicycle or a highway sign, but executed with a precision that borders on the impossible. The manufacturing process for these prisms was an exercise in extreme material science. Engineers at the Bendix Corporation and the Arthur D. Little Company had to ensure that the angles were accurate to within a fraction of an arcsecond. An arcsecond is a unit of angular measurement equal to 1/3600th of a degree. To visualize this, imagine the width of a human hair as seen from a distance of 20 meters. If the angle of the prism was off by even a tiny amount, the reflected laser beam would miss the Earth entirely, disappearing into the void. The technicians at the Bendix Aerospace Systems Division worked in clean rooms that were more sterile than a surgical theater. Each prism had to be polished with a diamond slurry for hundreds of hours to achieve a surface that was flat to within a wavelength of light. The silica glass itself had to be incredibly pure to withstand the harsh environment of the lunar surface. The temperature on the moon swings from 100 degrees Celsius in the sun to negative 170 degrees Celsius in the shade. These extreme thermal gradients can cause the glass to expand and contract, warping the geometry of the mirrors. To combat this, designers used Suprasil, a synthetic fused silica with a very low coefficient of thermal expansion. This material is essentially a liquid that has been frozen into a state of perfect stillness. This simple technology allowed scientists on the Earth to do something extraordinary. Researchers could fire a laser beam at the moon and wait for the echo. This process, known as lunar laser ranging, or LLR, transformed the moon into a giant laboratory. The history of this project is a demonstration of international cooperation and scientific persistence. Following the Apollo 11 mission, later, missions like Apollo 14 and Apollo 15 deployed even larger arrays. The Apollo 15 array, in particular, is the largest of the three, containing 300 individual corner cube prisms. The Soviet Union also contributed to this lunar network, placing French-built reflectors on the Lunokhod 1 and Lunokhod 2 rovers. The Lunokhod missions were marvels of robotic exploration, controlled by operators on the ground who had to navigate the craters and boulders of the lunar surface using low-resolution television cameras. For over 50 years, observatories like the McDonald Observatory in Texas and the Observatoire de la Côte d'Azur in France have fired trillions of photons into the night sky. The objective was simple: measure the distance to the moon with the precision of a ruler. But as the decades passed and the data accumulated, the ruler revealed a pattern that the laws of physics could not easily explain. The mechanical reality of lunar laser ranging is a feat of extreme photon management. A laser pulse leaves a telescope on the Earth with a power of several gigawatts. This pulse is a concentrated burst of light packed with billions of trillions of photons. As the beam travels through the atmosphere of the Earth, the light begins to spread. Turbulence in the air, caused by pockets of warm and cold gas, scatters the light like a lens made of moving water. By the time the pulse reaches the moon, the beam has expanded to a circle several kilometers wide. Most of those photons hit the lunar dust and are lost forever. Only a tiny fraction strike the silica mirrors. That fraction then reflects back toward the Earth, spreading even further during the return journey. When the signal returns to the telescope, the beam is several kilometers wide again. The telescope captures only a handful of photons. In many cases, a single pulse consisting of a quintillion photons results in the detection of exactly one returning photon. A single particle of light is the ghost in the machine. To catch one photon, researchers use a device called a photomultiplier tube. The instrument is so sensitive that the arrival of a single particle of light triggers a cascade of electrons, creating a measurable electrical pulse. The photomultiplier works by accelerating a single photoelectron through a series of electrodes called dynodes. Each time the electron strikes a dynode, the collision releases more electrons, creating an exponential increase in current. The process turns a single invisible photon into a surge of electricity that can be recorded by a computer. Imagine trying to hear the sound of a single snowflake falling in the middle of a thunderstorm, and then using that sound to calculate the height of the clouds. By measuring the round-trip travel time of that single photon using atomic clocks, researchers can calculate the distance to the moon with a precision of a few millimeters. The measurement is not a one-time event. A continuous dialogue spanning 50 years connects the Earth and the Moon. The dataset is the most accurate record of celestial motion ever recorded by human hands. To appreciate the difficulty of this measurement, consider an analogy involving a moving vehicle. Imagine a car is driving along the horizon several kilometers away. In the middle of a pitch-black night, you are standing in a dark field with a rubber ball. Your task is to throw the ball at the car, have the ball bounce off the rear-view mirror, and catch the ball when the object returns to your hand. Now, imagine the car is moving at thousands of kilometers per hour. The ball travels at the speed of light, but the distance is so vast that the car has moved several kilometers by the time the ball reaches the target. You have to lead the target, aiming where the car will be in 1.3 seconds. And you have to do this while standing on a platform that is also spinning and moving. If you catch even one ball out of a trillion throws, you have succeeded. This is the daily reality for the researchers at the Apache Point Observatory in New Mexico, where the 3.5-meter telescope is powerful enough to detect these tiny whispers of light. The precision of this system allows for the detection of subtle shifts that would be invisible to any other instrument. For decades, the data seemed to follow the predictions of general relativity perfectly. The moon is spiraling away from the Earth at a rate of 3.8 centimeters per year. The retreat is well understood. Tidal friction drives the movement. As the moon pulls on the oceans of the Earth, the rotation of the planet slows down. The gravity of the moon drags the tidal bulge of the Earth forward, ahead of the line connecting the two bodies. A forward-leaning bulge exerts a gravitational pull on the moon, accelerating the satellite in the orbit of the moon. As the moon moves faster, the body moves into a higher, more distant orbit. Standard physics explains the retreat. The clockwork of the universe is in motion. Now, a researcher might think that a 3-centimeter shift is a minor detail, but in the world of precision astrometry, 3 centimeters is a canyon. If the moon moved even a few millimeters differently than the models predicted, the discrepancy would stand out like a red flag in the data. For nearly 40 years, the red flag remained hidden. But in 2009, 2 researchers at the Jet Propulsion Laboratory, James Williams and Dale Boggs, published an analysis that changed everything. The team looked at 38.7 years of LLR data, covering the period from March 1970 to November 2008. This analysis used the DE421 ephemerides, the most sophisticated mathematical model of the solar system ever created. But the data showed a secular increase. The moon is moving away, while the satellite simultaneously becomes more erratic. The orbit is stretching. Currently, the measured rate of increase is 9 times 10 to the minus 12 per year. Now, that number sounds small. To a person on the street, 9 times 10 to the minus 12 is essentially zero. But to the experts at the Jet Propulsion Laboratory, the signal is significant. The value is statistically significant at a 3 sigma level. In statistics, the sigma value represents the standard deviation. A 1 sigma result means a 32% chance exists that the result is just random noise. A 2 sigma result reduces that chance to 5%. But a 3 sigma result means only a 0.3% chance remains that the detected drift is a fluke. In the world of high-stakes physics, 3 sigma is the threshold where a curiosity becomes a discovery. This means a 99.7% chance exists that the drift is real and not merely a fluke in the data. Williams and Boggs were not seeing noise. The researchers were seeing a physical reality that should not exist. The scale of this anomaly is staggering when one considers the implications. If the orbit is stretching, the moon is experiencing a force that is pulling the satellite harder at the furthest point and less at the closest point. The mystery deepened when Williams and Boggs tried to explain the shift using standard dissipation models. Dissipation is the process where energy is lost to heat. As the moon and Earth pull on each other, the rocks and oceans flex. This flexing generates heat, and that heat comes from the energy of the orbit. Researchers have very good models for how the core of the Earth and the mantle of the moon dissipate this energy. The dissipation models have failed. The standard view of the Earth-Moon interaction explains the distance, but the view fails to account for the shape. The moon is departing with a signature that contradicts the expected behavior of a two-body system. A discrepancy emerges that mirrors the 15-meter error. The scale is smaller, but the precision is higher. The anomaly is a sign that the fundamental laws of gravity, as applied to the local neighborhood of the Earth, are missing a variable. Consider the implications of a failing model. If the researchers at the Jet Propulsion Laboratory cannot explain the shape of the orbit of the moon, then the scientific community does not fully understand the relationship between the Earth and the closest companion of the Earth. This is the most studied gravitational pairing in the universe. We have placed mirrors on the surface. For half a century, lasers have bounced off those mirrors. Our understanding of the mass of both bodies has reached incredible precision. Yet, the moon is drifting away with a wobble that defies the math. The skeptical analysis of this anomaly is rigorous. Some researchers have suggested that the error might lie in the way the data is processed. Perhaps the researchers did not account for the way the crust of the Earth rises and falls with the tides. But the models already account for these solid-body tides. Others suggested that the shifting of the oceans is more complex than the models allow. But the ocean tide models are based on decades of satellite altimetry. The error margin in the tides is far smaller than the 9 times 10 to the minus 12 signal. This brings the investigation to the most uncomfortable possibility. If the error is not in the data and the error is not in the tides, then the error must be in the gravity. The moon is reacting to a force that is not included in the equations of Albert Einstein. This is the same conclusion that the researchers reached with the Viking lander residuals: a secular increase in distance, a secular increase in eccentricity. The solar system is expanding and stretching in ways that the mainstream narrative cannot explain. The precision required to detect this drift is almost incomprehensible. We are talking about a shift of a few millimeters per year in an orbit that is 384,000 kilometers wide. This is equivalent to measuring the thickness of a human hair from across a city. The fact that the scientific community can see this shift at all is a demonstration of the power of lunar laser ranging. But that power has revealed a truth that many would prefer to ignore. The lunar orbit is not a stable, predictable clock. The system is a changing, anomalous environment. This level of precision was pioneered at the McDonald Observatory, perched on Mount Locke in the Davis Mountains of West Texas. The history of this facility is a saga of persistence against the limitations of light. Founded in 1939, the observatory was built in one of the darkest spots in North America. The air is dry and thin, providing a clear window into the heavens. In the 1960s, the 82-inch Otto Struve telescope was equipped with a laser system to begin the first ranging experiments. The early researchers had to fire the laser manually, timing the pulses with primitive electronics. The return signal was so weak that the team often spent entire nights without a single confirmed detection. But the scientists refused to give up. The researchers understood that even a single photon could reveal the secrets of the universe. Now, a skeptic might ask why this matters. If the moon is only wobbling by a few millimeters, why should anyone care? But here is the thing. In physics, an anomaly is never just a small error. An anomaly is a loose thread. If you pull on the thread, the entire fabric of the understanding of the universe might unravel. If the moon is moving because of dark matter, or modified gravity, or a hidden planet in the outer solar system, then our entire map of the cosmos is wrong. This is the wonder spike of precision. The closer the observer looks, the more the reality of the universe begins to fragment. The stretching of the lunar orbit suggests that the very geometry of space is not as rigid as once believed. Imagine aiming a rifle at a target. The target is a single penny, and the penny is sitting on the surface of the moon. To hit that penny, your aim must be perfect. You have to account for the rotation of the Earth, the wind, the curvature of the planet, and the gravitational pull of the sun. Now, imagine you fire the shot and you hit the penny, but the bullet does not hit the center. The bullet hits the edge. You check your equipment. The rifle is perfect. The math is perfect, but the penny moved. This is the humility of being wrong by the breadth of a hair. The scientific community has hit the target. The researchers have measured the moon to the millimeter, but the penny is not where the equations say the penny should be. The target is drifting. The investigation is left with a choice. We can assume the rifle is broken, or we can accept that the ground is moving, and the data from the silver mirrors says the ground is moving. The transition from the moon to the wider solar system reveals that this is not a local problem. The lunar anomaly is just one layer of the mystery as we move further out, past the orbit of the moon and into the deep space between the planets. The anomalies become even more frequent. The probes that humanity has sent to the outer reaches of the solar system are also reporting strange behavior. Probes like Pioneer and Galileo, machines designed to follow the paths of general relativity, are drifting off course. But the mystery extends beyond the moon to the probes leaving the sun. The investigation must now look at the spacecraft that have ventured into the dark. These machines have detected an unexplained acceleration that mirrors the expansion found on Mars and the wobble found on the moon. The pieces do not fit, and the deeper we go into the void, the stranger the evidence becomes. We must now examine the Pioneer anomaly and the Earth flyby gains to see if the missing meters are a universal sign of a hidden physics. This is the evidence layer of the investigation. The moon is departing, and the satellite is not leaving quietly. The Silver Companion is leaving a trail of numbers that suggest the solar system is a much more mysterious place than the history books claim. We are standing on a planet that is drifting away from the sun, while the moon of the Earth stretches the orbit of the moon in a silent mathematical protest. The investigation continues into the outer dark, where the probes are waiting to tell their own story of the missing meters. This concludes our second stage of analysis. The investigation into the missing meters now leaves the silver light of the moon and moves into the deep cold of interstellar space. Beyond the reach of any telescope, two machines are reporting a reality that contradicts the known laws of motion. These machines are Pioneer 10 and Pioneer 11, the first human ambassadors to the outer planets. While the lunar mirrors provided a precise record of the local neighborhood of the Earth, the Pioneer probes offer a glimpse into the behavior of gravity across billions of kilometers. These spacecraft were launched into a universe that the scientific community believed was a stable, predictable clockwork mechanism. But as the probes crossed the threshold of the outer solar system, the clock began to run slow. The data revealed a sunward acceleration that should not exist. The pieces of the cosmic puzzle do not quite fit, and the deeper we look into the void, the more the official narrative begins to unravel. The history of the Pioneer missions is a saga of exploration that redefined the understanding of the solar system. On March 2, 1972, Pioneer 10 lifted off from Cape Canaveral on a journey to Jupiter. This mission was a leap into the unknown, tasked with surviving the intense radiation belts of the largest planet in the system and the hazards of the asteroid belt. Just over a year later, on April 5, 1973, Pioneer 11 followed a similar path, destined for a close encounter with both Jupiter and Saturn. These spacecraft were designed by the Ames Research Center and managed by a dedicated team of engineers who had to navigate the probes through millions of kilometers of empty space using the most primitive computers of the era. For decades, the missions were celebrated as absolute successes. The probes sent back the first close-up images of the gas giants, revealing the swirling storms of Jupiter and the intricate rings of Saturn. But in the late 1980s, a researcher at the Jet Propulsion Laboratory noticed a red flag in the telemetry. John Anderson, a senior scientist with a reputation for extreme mathematical rigor, began to see a discrepancy in the Doppler shift of the radio signals returning from the spacecraft. As the probes moved away from the Earth, the frequency of the signals should have decreased by a predictable amount due to the expansion of the distance. This is the same principle as the sound of a siren dropping in pitch as an ambulance passes a bystander. But the signal from the Pioneer probes was slightly higher in frequency than the models predicted. The light was shifting toward the blue end of the spectrum. This meant the probes were not moving as fast as the equations of Albert Einstein suggested. Some invisible force was tugging on the machines, pulling the probes back toward the sun. This phenomenon became known as the Pioneer anomaly. For 15 years, John Anderson and a team of specialists at the Jet Propulsion Laboratory examined the data, searching for an error in the software or a glitch in the hardware. The team looked at every possible source of error, from the gravitational pull of unknown asteroids to the pressure of the solar wind. But the sunward acceleration remained constant, a silent signature of a missing physics. The mechanical reality of the Pioneer anomaly is defined by a value that has haunted the halls of the Jet Propulsion Laboratory for decades. The acceleration is equal to 8.74 times 10 to the minus 8 centimeters per second squared. Now, to a person on the ground, that number is effectively zero. This is an acceleration so tiny that the probe would take over 1,000 years to reach the speed of a walking human. But in the vacuum of space, where gravity is the only master, this tiny drift is a massive signal. The measurement was made using the Deep Space Network, or DSN, a global network of giant radio antennas located in California, Spain, and Australia. These antennas are capable of tracking the position of a spacecraft with a precision of a few meters over a distance of billions of kilometers. The DSN operates by measuring the phase of the radio waves as the waves travel through space. By comparing the phase of the transmitted signal with the phase of the received signal, researchers can determine the velocity of the probe to within a fraction of a millimeter per second. This is like standing on the Earth and measuring the speed of a bumblebee flying around a light bulb on the moon. The precision of the tracking system revealed that the sunward acceleration was perfectly uniform. No sudden lurch or momentary glitch appeared in the data. A steady, relentless pull lasted for 30 years. Every time the researchers checked the data, the 8.74 value was there. Engineers checked the orientation of the spacecraft. Technicians examined the temperature of the fuel lines. Scientists even verified the mass of the probes to account for the fuel consumed by the thrusters. But no matter how many variables the researchers added to the equations, the sunward drift persisted. Williams and Boggs had experienced the same frustration with the moon. The data was perfect, but the model was failing. The expansion of the solar system was merely the first symptom. The very laws of motion appeared to be shifting alongside the measurement of distance, drifting into the dark as the fundamental models began to fail. To understand the magnitude of this error, consider an analogy involving a coasting vehicle. Imagine you are driving a car on a perfectly flat, level highway in the middle of a desert. You put the car in neutral and allow the vehicle to coast. You have calculated exactly how far the car will travel based on the weight of the vehicle, the friction of the tires, and the resistance of the air. You expect the car to stop at a specific milestone 5 kilometers away. But as the car slows down, you notice something strange. The vehicle is losing speed faster than the math allows. You check the brakes. The brakes are not touching the wheels. You check the road. The pavement is perfectly smooth. Yet every second, the car is losing a tiny bit more momentum than the laws of physics predict. The scenario suggests that an invisible hand is reaching out from the horizon and gently pulling on the bumper. If you do this experiment over and over, and the car always stops 10 meters short of the milestone, you have a problem. You have to admit that either your understanding of friction is wrong or an invisible force is acting on the car. This is the Pioneer anomaly. The spacecraft were coasting through the desert of space, and the machines were stopping short. The mystery of this sunward pull became even more confusing when researchers compared the Pioneer data to the Voyager probes. Voyager 1 and Voyager 2 followed similar paths into the outer solar system. Yet these probes did not report a similar sunward acceleration. This was the contradiction that divided the scientific community. Why would gravity act on Pioneer but ignore Voyager? The answer might lie in the way the machines were built. The Pioneer probes were spin-stabilized. Like a giant top, the spacecraft spun at a rate of 5 revolutions per minute to maintain a stable orientation in space. This design allowed the probes to keep the high-gain antennas pointed toward the Earth without the need for active thrusters. The Voyager probes, by contrast, were 3-axis stabilized. These machines used active gyroscopes and small thrusters to maintain a fixed position. The constant firing of these thrusters created a noisy environment in the telemetry, making detection much harder to detect a tiny acceleration like the one found on Pioneer. But many researchers argued that the difference in design should not matter if the force was gravitational. Gravity does not care how a spacecraft is stabilized. If the sun is pulling harder than the equations allow, then every object in the solar system should feel the same tug. The philosophical weight of this navigation error is profound. If the human species cannot navigate a simple probe through the backyard of the Earth without losing track of the position of the probe, what does that say about our mastery of the cosmos? The Pioneer anomaly is a humbling reminder that the maps of the universe are only approximations. We have built giant antennas and atomic clocks to measure the movements of the planets, yet we are still surprised by a drift that is smaller than the width of a fingernail. The anomaly suggests that the vacuum of space is not truly empty. This void might be filled with hidden actors or unknown forces that we are only beginning to perceive. The missing meters are a signal that the universe is not as predictable as the textbooks claim. The drift of the Pioneer probes is a silent message from the dark, telling us that the rules of the game are changing. While the Pioneer probes were reporting a sunward pull in the outer solar system, another mystery was unfolding much closer to home. The anomaly did not involve a steady drift over decades. A sudden violent surge in energy appeared in the data. The phenomenon is known as the flyby anomaly, and the data was first detected during the gravity assists of several high-profile missions in the 1990s and early 2000 years. A gravity assist is a cosmic slingshot. Spacecraft flies close to a planet using the gravity of the body to gain velocity and change direction. This maneuver is a standard tool of celestial navigation, allowing probes to reach distant targets like Jupiter or Saturn without carrying massive amounts of fuel. But when the Galileo spacecraft flew past the Earth in December 1990, the machine emerged from the encounter with more energy than the laws of physics allowed. The Galileo mission was a flagship project of the National Aeronautics and Space Administration, destined for a long-term study of Jupiter and the many moons of the giant planet. To reach the destination, the probe had to fly past the Earth twice, gaining speed with each encounter. During the first flyby, the researchers at the Jet Propulsion Laboratory noticed a sudden jump in the Doppler frequency of the signal. The probe had gained an extra 4 millimeters per second of velocity. This shift is almost imperceptible. A millimeter per second is the speed of a slow-moving insect, but in orbital mechanics, a 4-millimeter shift is a disaster for the models. An increase in speed means the probe is on a different trajectory than the one the engineers planned. If the speed is wrong, the probe will arrive at the destination at the wrong time or in the wrong position. The researchers checked the data again. The jump was real. The mystery deepened in January 1998 when the Near-Earth Asteroid Rendezvous spacecraft, or NEAR, flew past the Earth. The probe was designed to study the asteroid Eros, and the flyby was a critical part of the journey. As the NEAR probe reached the point of closest approach, the velocity jumped by 13 millimeters per second. The jump was 3 times larger than the surge seen by Galileo. The researchers were baffled. The team looked for any possible explanation. Was there an error in the way the rotation of the Earth was modeled? Was the gravity of the Earth slightly different than we thought? But the NEAR probe was tracked by multiple antennas, and the jump appeared in every dataset. The probe had simply gained energy from nothing. In the years that followed, other missions reported similar surges. The Rosetta probe, a mission to land on a comet, gained 2 millimeters per second in 2005. Each time, the surge occurred at the moment of closest approach, or perigee. The mechanical reality of the flyby anomaly is defined by a shift in the hyperbolic trajectory of the spacecraft. When a probe flies past a planet, the path is a curve known as a hyperbola. The probe approaches from infinity, curves around the planet, and then heads back out into space. According to the equations of general relativity, The incoming speed and the outgoing speed should be identical relative to the planet. The energy is conserved. But the flyby probes were emerging from the perigee with a higher velocity than the machines possessed when the encounter began. This meant the probes had gained kinetic energy from a source that did not appear in the equations. The anomaly was not random. The researchers noticed a pattern. The size of the velocity jump seemed to depend on the angle of the approach and the latitude of the perigee. Probes that approached the Earth at a steep angle showed a larger jump than those on a shallow path. This suggested that the anomaly was related to the rotation of the planet or the way the gravity of the Earth interacts with moving objects. To understand the flyby anomaly, imagine a cosmic slingshot. You have a ball attached to a string, and you are spinning the ball around your head. As the ball moves, you can pull on the string to change the path of the ball. In this analogy, the string is gravity. If you let go of the string, the ball flies off in a straight line. If you pull the string in, the ball moves faster. Now, imagine you are standing on a spinning platform. As you spin the ball, you notice that the ball gains a little bit of extra speed every time the object passes a certain point in your rotation. You are not pulling the string any harder. The platform is not moving any differently. Yet, the ball is gaining energy. This is what is happening to our spacecraft. The Earth is the spinning platform, and the probes are the balls on the string. Every time the probes pass the perigee, the machines gain a tiny, unexplained boost. The data implies that the spinning of the Earth is imparting energy to the probes through a mechanism that we do not yet understand. The most frustrating part of this discovery is that the anomaly only seems to appear during flybys of the Earth. When the Cassini probe flew past Venus and Jupiter, the data matched the models perfectly. No unexplained surges were detected. This has led some researchers to suggest that the anomaly is a detection problem rather than a physical reality. Perhaps the models of the atmosphere of the Earth are wrong, or perhaps the way we measure the rotation of the Earth is slightly off. But the Earth is the most measured object in the universe. We have a global network of global positioning system satellites and atomic clocks that can measure the rotation of the planet to within a microsecond. The idea that we have missed a fundamental detail in the neighborhood of the Earth is hard to accept. Yet, the flyby anomaly persists, a silent witness to a gap in our mastery of gravity. The detection problem is the core of the mystery. To understand the missing meters, researchers must be able to separate the signal of gravity from the noise of the environment. In space, many things can push a spacecraft. The solar wind, a stream of charged particles from the sun, exerts a constant pressure on the surface of the probe. Thermal radiation, the heat generated by the electronics and the nuclear power sources of the spacecraft, also creates a tiny thrust as the heat radiates into the void. For years, skeptics argued that the Pioneer anomaly was not a mystery of gravity, but a mystery of heat. This debate led to one of the most exhaustive forensic investigations in the history of science. Slava Turishev, a researcher at the Jet Propulsion Laboratory, spent over a decade recovering the original telemetry data from the Pioneer missions. This was a monumental task. Much of the data was stored on obsolete magnetic tapes in a format that modern computers could not interpret. Some of the tapes were rotting in storage bins. Turishev had to track down the original programmers and find the vintage hardware required to extract the information. The goal was to build a complete thermal model of the Pioneer spacecraft. The team wanted to know exactly how every watt of heat was radiating from the machine. The Pioneer probes were powered by radioisotope thermoelectric generators, or RTGs. These devices use the decay of plutonium to generate heat, which is then converted into electricity. As the plutonium decays, the heat output slowly decreases. The mechanical reality of the thermal model is based on the geometry of the spacecraft. The RTGs were mounted on long booms, away from the main body of the probe. As the heat radiated from these generators, some of the infrared photons struck the back of the high-gain antenna, which acted like a giant reflector. This reflected heat would exert a tiny pressure on the spacecraft, pushing the machine in the opposite direction. If more heat was radiating toward the back than the front, the probe would experience a net thrust. Turyshev and his team built a sophisticated computer model that accounted for every component of the spacecraft, from the louvers on the electronics bay to the texture of the insulation blankets. The results, published in 2012, suggested that the thermal thrust could explain much of the Pioneer anomaly. As the heat output of the RTGs decreased over time, the sunward acceleration also appeared to decrease in a way that matched the data. To understand the thermal thrust, imagine a flashlight mounted on a skateboard in a perfectly dark, vacuum-sealed room. When you turn on the flashlight, the photons leaving the bulb exert a tiny pressure on the skateboard. This is radiation pressure. The skateboard will begin to move very slowly in the opposite direction. Now, imagine the flashlight is very hot and the device is radiating heat in all directions. If you place a mirror behind the flashlight, some of that heat will reflect forward, increasing the pressure. The skateboard will move faster. This is what Turyshev argued was happening to Pioneer. The heat from the nuclear generators was reflecting off the back of the antenna, creating a tiny, persistent push that mimics a sunward acceleration. While early analysis pointed to a mystery of gravity, newer models suggested the culprit was actually heat. The mystery of Pioneer seemed to be solved. The pieces finally fit. But the skeptical analysis reveals a fatal flaw in the thermal solution. If the Pioneer anomaly is caused by heat, how do we explain the flyby anomaly? Spacecraft like Galileo and Near were built with completely different geometries and power sources. These probes did not have large antennas acting as thermal reflectors. Furthermore, the flyby anomaly is a sudden surge in energy that occurs over the course of a few minutes, while the Pioneer anomaly is a steady drift over decades. A thermal model that explains a slow drift cannot explain a sudden surge. This is the contradiction that keeps the investigation alive. We have a solution for one machine that fails for the others. This brings us to the failure of the thermal model as a universal explanation. The researchers at the Jet Propulsion Laboratory have successfully modeled the heat of Pioneer, but the team has not solved the mystery of the missing meters. The expansion of the astronomical unit remains unexplained, and the stretching of the lunar orbit continues to defy the dissipation models. We have found a reason to ignore one anomaly, but we have not found a reason to ignore the pattern. The pattern suggests that something fundamental is happening to the way we perceive distance and gravity in the solar system. The skeptical analysis must be as rigorous as the investigation itself. Victor Toth, a software engineer and physicist who worked with Turyshev on the Pioneer model, is a leading voice for the thermal explanation. Toth argued that the complexity of the spacecraft makes any gravitational explanation unlikely. The researchers found that the sunward acceleration was not perfectly constant. The value was decaying over time. This decay is the signature of a thermal source. As the plutonium in the RTGs decays, the heat output drops and the thrust decreases. If the force were gravitational, the value should be independent of the power source of the spacecraft. This is a powerful argument. The thermal model is the most rational, most grounded explanation for the behavior of the Pioneer probes. The limits of human measurement are being tested. We have built machines that can detect the heat of a single photon and the drift of a millimeter, yet we are still arguing over the results. The detection problem represents more than a technical challenge. The detection problem is an intellectual one. We are biased toward explanations that fit our existing models. We want the answer to be heat or noise or a glitch in the software. We do not want the answer to be that our understanding of gravity is fundamentally incomplete. But the data from the flyby probes is a stubborn reminder that the universe does not always follow our rules. The surge of energy at the perigee of the Earth is a signal that we are missing something profound about the relationship between motion, rotation, and the fabric of space. The search for the hidden actors is the next step in the investigation. We have seen the anomalies in the radar ranging and the wobble in the lunar orbit. Now, we have seen the drift and the surge in the deep space probes. The pieces do not fit, and the official narrative is exhausted. We are left with a solar system that is expanding and accelerating in ways that defy the laws of Einstein. This brings us to the hidden weight. If the laws of gravity are correct, then there must be more mass in the system than we can see. We must look for dark matter or hidden planets, or a fundamental shift in the geometry of the universe. The investigation continues. The probes are still out there, coasting into the dark, silent witnesses to a reality that we are only beginning to understand. The missing meters are not an error. These discrepancies represent a map to a new physics. We must follow that map, even if the path takes us beyond the edge of our understanding. The truth likely lies somewhere between the data and the doubt, and that ambiguity is what keeps us looking at the stars. The next stage of the investigation will take us into the domain of the invisible, where the hidden weight of the solar system waits to be discovered. This brings us to the search for the hidden actors. The investigation into the missing meters now moves from the visible machines to the invisible architecture of the galaxy. The discrepancy in the astronomical unit suggests that our star is not the isolated furnace we once imagined. Instead, the proposal suggests that the sun is a gravitational vacuum cleaner, gathering the invisible mass of the universe as our solar system orbits the galactic center. This process, known as dark matter accretion, would fundamentally change the mass of the sun, and by extension, the orbits of every planet. The context for this investigation begins with the realization that the sun is constantly losing mass. Through solar wind and electromagnetic radiation, the star sheds approximately 6 billion kilograms of material every second. According to the laws of celestial mechanics, this loss of mass should cause the gravitational grip of the sun to weaken. The planets should drift outward, but the math predicts a change of only 0.3 centimeters per year. This value represents a tiny fraction of the 15-meter expansion reported by Krasinsky and Brumberg. The search for the missing weight led Iorio to consider the influence of weakly interacting massive particles, often abbreviated as WIMPs. These hypothetical particles are the primary candidates for dark matter, and they are believed to fill the void of the galaxy. The measurement of this accretion rate is a challenge for modern astrophysics. Iorio calculated that if the sun captures dark matter at a specific rate, the increase in gravitational pull would counteract the expansion of the orbits. But here is where the mystery deepens. The data from the astronomical unit expansion suggests that the planets are moving outward faster than the mass loss allows. This data implies that the hidden weight must be acting in a way that mimics an expansion rather than a contraction. The math of Iorio reveals that the secular increase of the astronomical unit might be an artifact of how we measure mass and distance in a changing system. The sun is gaining weight, but the yardstick we use to measure the solar system is stretching even faster. To understand this accretion process, imagine a sponge being pulled through a thick, invisible fog. The sponge represents the sun, and the fog represents the dark matter of the galaxy. As the sponge moves, most of the fog passes through the holes, but a few droplets of moisture cling to the fibers. Over time, the sponge becomes heavier. You cannot see the water, and you cannot see the fog, but the weight of the sponge increases steadily. If you are a tiny creature residing on a marble orbiting that sponge, you would notice that the orbit is changing. You might think the sponge is pushing you away, but in reality, the gravitational relationship is shifting because the central mass is no longer constant. The sponge is gathering the invisible weight of the void. This accretion theory raises a profound anomaly. If the sun is gathering dark matter, then every star in the galaxy should be doing the same. The models of stellar evolution would have to be rewritten to include the heating effects of dark matter annihilation in the cores of stars. Furthermore, the search for the capture rate of the sun has failed to find a signal that matches the required mass gain. The researchers are left with a contradiction. The expansion of the astronomical unit is a massive signal, but the evidence for the dark matter required to cause the expansion remains elusive. The components of the mystery refuse to align. The mystery of the invisible collector suggests that the star is gaining weight from a source that the sensors cannot detect. The existential implication of the gain is humbling. Our star is not a closed system. The sun is connected to the dark architecture of the universe, feeding on the invisible material that binds galaxies together. Connection means that the history of the solar system is tied to the movement of the sun through the galactic halo. Every time our solar system passes through a dense patch of dark matter, the expansion rate of the planets might shift. The missing meters are a signal that we are part of a much larger mechanism. The star is gaining weight, and the solar system is drifting because we are traveling through a sea of invisible mass that we are only beginning to perceive. The context for this filter comes from the work of researchers like Standish and Pijeva. These astronomers use a system of units where the astronomical unit is a fixed constant. When the radar data shows that a planet is not where the model predicts, the software interprets the shift as a change in the scale of the solar system. Iorio proposed that the 15-meter expansion is actually a signal of mass gain. If the sun is gathering mass at a rate of 1 part in 10 to the power of 13 per year, the resulting shift in orbital timing would perfectly match the reported expansion of the yardstick. This relationship creates a fascinating paradox. The star is getting heavier, which should pull the planets closer. But the way we measure distance makes the planets appear to be moving away. The mechanical reality of the filter is rooted in the definition of the Gaussian gravitational constant. The constant relates the orbital period of a planet to the distance from the sun. For centuries, the value was considered a fundamental anchor of astronomy. But as the precision of our measurements improved, the anchor began to drag. Researchers found that they could no longer fit the data from the inner planets without allowing the astronomical unit to drift. The drift is the signature of a system where the mass and the distance are coupled in a way that the standard models do not account for. The mass accretion of dark matter provides a physical mechanism for this shift, acting as a hidden driver for the expansion of the scale. This realization leads to a humbling conclusion about our mastery of the solar system. We have spent centuries perfecting the maps of the planets, yet we are still struggling to define the length of our own yardstick. The expansion of the astronomical unit is a signal that our fundamental units of measure are tied to a central mass that is not stable. The star is changing, and as a result, the distance is changing. The missing meters are a reminder that the solar system is not a static clockwork mechanism. The star is an existing, breathing machine that is interacting with the invisible architecture of the galaxy. The yardstick is stretching because the star is gaining weight from the void. The third stage of the investigation takes us to the remote peripheries of the solar system, where a different hidden actor might be at work. This stage is the search for Planet X, a putative, massive body that exists far beyond the orbit of Neptune. In 2011, Lorenzo Iorio used the anomalous precession of the perihelion of Saturn to put constraints on the location of this hidden planet. At the time, data from the Cassini spacecraft suggested that Saturn was experiencing a tiny, unexplained wobble in the orbit of the planet. This wobble could be the gravitational signature of a distant object pulling on the ringed planet. If a large planet exists in the outer dark, the gravity of that body would create a persistent tug that mimics the secular expansion of the inner solar system. The mechanical reality of a Planet X perturbation is defined by the tidal parameter of the distant body. A distant planet exerts a primary pull on the Sun, while simultaneously tugging on every object in the solar system. This pull creates a secular variation in the eccentricity and the perihelion of the planetary orbits. Iorio calculated that an Earth-sized planet located at 250 astronomical units would produce a gravitational signal that matches the reported anomalies in the inner solar system. Similarly, a Jupiter-sized body at 3,500 astronomical units would create the same effect. The mystery is that we cannot see this planet. The Wide Field Infrared Survey Explorer, or WISE, scanned the entire sky in the infrared and found no heat signature of such a world. The anomaly of the Planet X candidate is that the constraints are becoming tighter every year. The latest analyses of the Saturnian perihelion by Fienga and Picheva show no anomalous precession that would require a distant planet. This finding implies that if Planet X exists, the body must be even further away or much smaller than the models suggest. But if the planet is too small, the mass cannot explain the expansion of the astronomical unit. We have a gravitational signal that requires a massive actor, but a sky that appears empty of any such intruder. The mystery of the hidden planet suggests the missing meters might have a different origin. The existential weight of this search is profound. If a massive planet has been hiding in our own backyard for billions of years, our understanding of the solar system is fundamentally incomplete. The neighborhood of the Earth is still full of secrets. We have sent probes to the edge of the void, yet we might have missed a world as large as Jupiter. The missing meters signal that the architecture of the solar system is more complex than the maps show. The yardstick is stretching, and the planets are wobbling because we are not alone in the dark. The final stage of this investigation brings us to a synthesis of the local and the global. In 2011, Lorenzo Iorio proposed an empirical formula that attempts to unify the expansion of the astronomical unit, the lunar eccentricity anomaly, and the drift of the Pioneer probes. The proposal suggests that an extra radial acceleration exists, acting on every object in the solar system. This acceleration is proportional to the radial velocity of the object and a value that is suspiciously close to the Hubble constant. This is the Hubble-like expansion model, implying that the expansion of the universe is manifesting within the local neighborhood of the Earth. The context for this synthesis is the long-standing debate over whether the expansion of the universe affects local systems. According to General Relativity, the expansion of space happens on a galactic scale, but the local gravity of the solar system should be strong enough to bind the planets together. The space between the Sun and the Earth should not be expanding. However, Iorio found that an acceleration equal to the Hubble parameter, multiplied by the radial velocity of the planet, produces a secular increase of the astronomical unit of a few centimeters per year. This matches the reported expansion rate almost perfectly. The cosmic scale is leaking into the planetary scale. The mechanical reality of this Hubble like acceleration is defined by the formula A equals k multiplied by h0 multiplied by vr. In this equation, h0 is the Hubble constant, measuring the rate at which galaxies move away from each other. Vr is the radial velocity of the planet. Iorio found that a value for k between 2.5 and 5 would explain both the astronomical unit expansion and the anomalous increase in the eccentricity of the Moon. This empirical formula is a pattern found in the data, a correlation that defies the textbooks. The solar system appears to be expanding at a rate tied to the age and scale of the entire universe. The mystery of this synthesis is that the correlation contradicts the Einsteinian model of the universe. In the Friedmann-Lemaitre-Robertson-Walker metric, the local gravitational field is isolated from the global expansion. The yardstick of the solar system should be immune to the stretching of space, but the data suggests this isolation is an approximation. If the astronomical unit is expanding because of the Hubble constant, then the fundamental laws of gravity must include a cosmological term acting at every scale. This connection would be a revolution in physics, moving the solar system from a stable clockwork to a changing participant in the cosmic expansion. To understand this synthesis, imagine a large sheet of rubber being stretched in all directions. On that sheet, you have drawn a tiny circle. In a perfect world, the rubber inside the circle would be held in place, and the circle would stay the same size as the sheet stretches. But in reality, the rubber is a single material. As the sheet stretches, a tiny bit of that tension is felt inside the circle. The circle begins to expand, not because the ink is failing, but because the material of the universe is under tension. The solar system is that tiny circle, and the expansion of the yardstick is the signal that we are part of the stretching rubber. The cosmic expansion exists beyond the distant galaxies, manifesting here in the distance between the Sun and the Earth. This synthesis raises an uncomfortable question about the nature of our measurements. If the expansion of the universe is affecting the local yardstick, then every distance we measure is a moving target. The astronomical unit is no longer a fixed anchor. The astronomical unit is a dynamic value that is evolving with the cosmos. This shift implies that the history of the solar system is tied to the history of the universe in a way that the models of Newton and Einstein did not foresee. The search for the hidden actors has led us back to the most fundamental actor of all, the universe itself. The missing meters are the signature of a cosmos that is growing, and we are growing with the universe. The investigation into the hidden weight and the missing actors has reached a threshold. We have looked at the dark matter accretion that could change the mass of the sun. We have examined the hidden planets that could tug on the orbits of the planets. And we have confronted the possibility that the expansion of the universe is acting on the distance between the planets. None of these explanations is perfect. Each one leaves a residual error or a contradictory data point. The pieces refuse to resolve into a single, clean picture. But the pattern is undeniable. The solar system is expanding. The planets are drifting, and the yardstick is failing. The philosophical implication of this threshold is that we are witnessing the breakdown of the classical clockwork. The solar system is not a machine that was wound up at the beginning of time and left to run. The solar system is a dynamic, changing system that is reacting to the invisible forces of the galaxy and the cosmos. The expansion of the astronomical unit is merely the first line of a much larger story. The search for the hidden actors has revealed a universe that is heavier, stranger, and more connected than the models allow. And that brings us to the final threshold of this journey. The future of distance. The investigation into these missing meters has arrived at the ultimate boundary of our knowledge. We have analyzed the dark matter that might gather around the sun and the hidden planets that might pull from the outer dark. But these physical actors are only part of the story. The central insight of this journey is that the solar system is not a static clockwork mechanism. For centuries, the planetary neighborhood was viewed as a perfect machine, a set of orbits carved in stone by the hand of gravity. The data from researchers like Elena Picheva and Miles Standish reveals a different reality. The solar system is a changing system, a dynamic organism that is evolving in ways that the classical models cannot explain. The expansion of the astronomical unit is the signature of this evolution. The yardstick is failing because the neighborhood is no longer standing still. The analysis of more than 300,000 observations spanning 4 decades revealed that the astronomical unit is increasing by several meters every century. The measurement is not a random fluctuation, but a consistent drift that shows up in the orbits of every inner planet. To understand the transition from a clock to an organism, imagine an ancient grandfather clock that has kept perfect time for 100 years. You assume the gears are steel and the pendulum is a fixed length. But then, a laser measurement reveals that the wooden frame is slowly absorbing moisture and swelling. The gears are moving further apart and the pendulum is stretching. The clock is still running, yet the fundamental scale of the machine has changed. The system is like that grandfather clock. These planets are the gears, and gravity is the spring, but the entire structure is reacting to the invisible environment of the cosmos. The planetary neighborhood is not a fixed blueprint, but a vibrant, breathing arrangement of mass and energy. The history creates a problem for the models of planetary formation. If the Earth were much closer to the Sun in the past, the oceans should have boiled away. The contradiction implies that the expansion we are seeing today might be a recent phenomenon, or perhaps the expansion is part of a larger cycle that we are only seeing a fragment of. The pieces of the history and the pieces of the data do not quite fit. The existential implication is a shift in how humanity views the home of the species. We have existed with the illusion of an eternal stability, building our calendars on the idea that the sun and the earth are a permanent pair. But the missing meters tell us that the relationship is evolving. We are drifting through the void on a world that is slowly letting go of the center. The real question is whether the laws of gravity are universal or merely local approximations. Albert Einstein provided a set of equations that describe every movement from the fall of an apple to the collision of black holes. But the anomalies in the solar system suggest that these equations might be missing a term. Researcher Acedo investigated whether anomalous post-Newtonian terms could explain the expansion of the astronomical unit. This work explores the possibility that gravity behaves differently when the angular momentum of a central body is involved. If the data contradicts the theory must be re-examined. The history of scientific revolutions provides context for this reframe. When Isaac Newton published the Principia in 1687, the world believed the mystery of gravity was solved. For 200 years, the Newtonian model was absolute. But then, astronomers noticed a tiny error in the orbit of Mercury. The perihelion of the planet was shifting by 43 arcseconds per century more than Newton allowed. Einstein solved the Mercury anomaly by redefining gravity as the curvature of space and time. Today, the 15-meter expansion of the astronomical unit is the new Mercury anomaly. This drift is a signal that our current model of gravity might be another approximation. We are seeing the limits of the master theory. Acedo proposed that extra terms might exist, proportional to the product of the solar mass and the angular momentum. These terms are invisible at the scale of a laboratory, but over the distance of an orbit, the effects begin to accumulate. The research specifically explored a radial perturbation that arises from the interaction between the mass of the Sun and the rotation of the star. In the Standard Model, the mass creates the curvature, but the rotation of that mass is often treated as a negligible detail for planetary distances. Acedo found that a specific radial perturbation could account for both the expansion of the astronomical unit and the strange increase in the eccentricity of the Moon. The model does not require the introduction of dark matter or unseen planets. Instead, the math suggests that the rotation of the Sun is exerting a subtle, repulsive force that pushes the planets outward. A ghost in the equations emerges, a secular drift that Einstein did not include. Imagine a blueprint for a massive skyscraper. The blueprint is perfect for small buildings, but as the skyscraper grows taller, you realize the plan failed to account for the curvature of the world. General Relativity is the blueprint of the cosmos. The theory works for the orbits we have measured for centuries, but as our measurements become more precise, we are seeing the lean in the building. In 2011, Lorenzo Iorio pointed out that the rate of the astronomical unit expansion is numerically close to the Hubble constant. The Hubble constant measures the expansion of the entire universe. According to standard physics, the expansion of the universe should not affect the local solar system. The concept is known as the Einstein-Strauss vacuole, the idea that a gravitationally bound system like our own is isolated from the cosmic stretching of space. The gravity of the Sun is supposed to be strong enough to carve out a pocket of stability. Yet, the expansion rate of 15 meters per century is exactly what you would expect if the solar system were growing at the same rate as the cosmos. Is the alignment a coincidence? Or is the correlation a signal that the large-scale expansion of the universe is leaking into the local neighborhood? The pattern implies that the boundaries of our local physics are more porous than we believed, and the tension of the expanding universe is pulling on the planets themselves. The researchers are looking for a balance in a system that appears to be out of balance. The future of the inner planets depends on the resolution of this mystery. The existential implication is the humbling realization of our ignorance. We have claimed to understand the fundamental laws of the universe, but if we cannot explain the movement of the planets in our own backyard, our knowledge remains a fragile construct. The precision of modern astronomy has reached a paradoxical threshold. The instruments are so accurate that the measurements reveal the limits of the theories designed to interpret the data. Place of precision exposes another anomaly, another gap in the mathematical framework. The yardstick is failing because the laws of the universe are still being written. We are not the masters of gravity, but students who have just discovered that the textbook is missing the final chapter. The 15-meter expansion is a signal that the relationship between mass and distance operates on rules that humanity has not yet fully decoded. Orbits change because energy is being added or removed from the system. If the planets are moving outward, the planets are gaining orbital energy. This energy must come from somewhere, and the most likely candidate is the rotational energy of the Sun itself. Star slows down, the lost momentum is transferred to the planets, pushing the neighborhood outward. This secular exchange of energy means that every kilometer of distance gained is paid for by the slowing of the heart of the system. Every centimeter of expansion requires a physical price. Iorio found that the expansion of the astronomical unit is tied to the long-term stability of the inner planets. To understand this climax, imagine a fire burning in the center of a large, cold room. You are sitting in a chair at a comfortable distance. Assume that your chair is bolted to the floor, but then you realize that the floor is actually a slow-moving conveyor belt. pulling your chair away from the fire at a rate of a few millimeters per hour. You look back and see that the fire is smaller in the distance. You try to stop the chair, but no brakes exist. Eventually, you will reach the far wall of the room where the heat of the fire cannot reach you. The solar system is that room, and the expansion of the astronomical unit is the conveyor belt pulling us into the cold. The mystery is why the Earth has stayed within the habitable zone for so long if the system is constantly expanding. For 4 billion years, liquid water has flowed on the surface, and life has thrived in a narrow corridor of temperature and pressure. The balance suggests the existence of a feedback mechanism that we do not yet understand. Perhaps the expansion of the sun as the star ages is being balanced by the expansion of the orbits. As the sun grows brighter and hotter, the Earth moves further away, maintaining a fragile equilibrium that has allowed life to survive for billions of years. The researchers are looking for a balance in a system that appears to be out of balance. The future of the inner planets depends on the resolution of this mystery. The investigation into the expanding yardstick and the drifting planets has brought us to the edge of our understanding. This 15-meter error is a ghost in the gears of the cosmos, a signal that our mastery of gravity is incomplete. Our neighborhood is changing, and as a result, the future is uncertain. Our planet is a fleeting guest in the habitable zone. We have treated the world as a permanent home, but the world is a passenger on a drifting journey. We are witnessing the slow loosening of the solar bonds, a transition from a stable sanctuary to a dynamic voyage. The investigation into the expansion of the astronomical unit has revealed that the yardstick serves as more than a tool for measurement. This device records our departure. Our solar system is drifting into the dark, and we are going with the system. The truth is written in the missing meters. The investigation into the missing meters has arrived at the ultimate boundary of human knowledge. The analysis examined the dark matter that might gather around the sun and the hidden planets that might pull from the outer dark. But these physical actors are only part of the story. The investigation has traced a pattern of anomalies that spans decades and millions of kilometers. The journey began with the strange residuals of the Viking 1 lander on the surface of Mars in 1976. At the time, the silence of the Martian desert was absolute, and a radio signal traveled across the void, a thin thread of light connecting two worlds separated by millions of kilometers. Engineers waited for the first ping of data to return from the rusted surface, expecting total precision. The solar system was viewed as a clockwork mechanism, governed by the laws of Isaac Newton and Albert Einstein. Every planet followed a path written in mathematics, and error was not an option in a universe defined by celestial mechanics. Yet, a strange pattern emerged from the digital noise. Mars was not where the calculations said the planet should be. The red world was drifting into the dark. But here is the thing. This early detection by the Viking team provided the first hint that the astronomical unit, the fundamental yardstick of the cosmos, was not a fixed constant. The measurement of these missing meters relies on the technique of radar ranging. To understand this mechanism, imagine a person standing in a massive canyon, shouting a single word and timing how long the echo takes to return. In the solar system, scientists shout with powerful radio waves generated by klystron tubes the size of a person. They bounce these signals off the surfaces of planets and measure the time of flight with atomic clocks. Researchers at Goldstone and Acedo fired these pulses with staggering power, achieving accuracies of a few centimeters over gaps of millions of kilometers. However, the signal that returns is incredibly weak. Due to the inverse square law, the radio pulse that hits Venus is 1 trillion times weaker than a cell phone signal. Trying to catch this return is like trying to see a single birthday candle on the moon while standing in a floodlit stadium. For 40 years, researchers like George Krasinsky and Miles Standish used this method to map the neighborhood, finding that the planets are moving further apart. This drift of 15 meters every century is a consistent signal. The planets are not staying in their assigned seats. The gears of the clock are slowly moving away from the center. This secular increase in the astronomical unit implies that the fundamental scale of the solar system is shifting. This expansion extends to the orbit of the moon. Since the Apollo missions, lunar laser ranging has provided a continuous record of the distance between the Earth and the satellite. Astronomers fire laser pulses at reflectors left on the lunar surface and measure the time of return. The mechanical reality is a feat of extreme photon management. By the time the laser beam reaches the moon, the light has expanded to a circle several kilometers wide. Only a few photons strike the specific targets, like the prisms left by the Apollo 15 mission. When the signal returns, the beam is several kilometers wide again. Often, a single pulse consisting of a quintillion photons results in the detection of exactly one returning photon. A single particle of light is the ghost in the machine. By measuring the round-trip travel time of that single photon, researchers can calculate the distance to the moon with a precision of a few millimeters. The record reveals that the moon is moving away from the Earth at a rate of 3.8 centimeters per year. Standard physics explains this retreat as a result of tidal friction. But while tidal friction explains the distance, the friction fails to account for the shape of the orbit. The eccentricity of the lunar path is increasing. The change in the shape of the orbit is a ghost in the equations. The moon is retreating, but the satellite is also drifting in a way that suggests a missing force is at work in the gears of the system. The investigation then followed the Pioneer spacecraft into the outer dark. In the late 20th century, Pioneer 10 and Pioneer 11 were leaving the solar system. As they moved beyond Saturn, engineers noticed a tiny, unexplained deceleration. A sunward tug was pulling on the probes, as if gravity was stronger than the models allowed. For a decade, this Pioneer anomaly remained a major mystery. Researcher Slava Turishev spent years recovering the original telemetry, finding that heat radiating from the internal power sources created a recoil force that explained the tug. This thermal solution was a victory for the standard model, but the victory was short-lived. While heat might explain the outer probes, thermal radiation cannot explain what happened to spacecraft closer to home. During gravity assists around the Earth, probes like Galileo and Rosetta experience sudden surges in speed. These flyby anomalies involved energy gains that occurred in minutes, far too fast for thermal radiation to be the cause. The energy was coming from the gravitational interaction itself. The narrative remains incomplete. Investigation revealed that no single theory covers the expansion of the astronomical unit, the increase in lunar eccentricity, and the flyby energy gains simultaneously. The analysis examined the theory of dark matter accretion, which suggests that the sun captures a cloud of invisible particles as the star moves through the galaxy. The added mass would change the gravitational strength of the center and push the planets outward. Understand this. Imagine a carousel spinning in a park. If you slowly pile heavy sand onto the center of the carousel while the machine spins, the added weight changes how the horses move. But the density of dark matter required to explain 15 meters of expansion every century is far higher than what astronomers see in the rest of the galaxy. If that much dark matter existed around the sun, the dark matter would interfere with the movements of comets and the stability of the asteroid belt. The dark matter solution creates more problems than the theory solves. The findings suggest that the answer does not lie in hidden matter, but in hidden physics. A second major finding involves the modification of the laws of gravity. Researcher Acedo explored the possibility that general relativity is missing a term related to the angular momentum of the Sun. In 1687, Isaac Newton provided the first map of gravity. In 1915, Albert Einstein updated that map by showing that mass curves space and time. But every map is an approximation. Acedo proposed that the rotation of the Sun creates a subtle repulsive force that acts on the planets over long time scales. Look at this. The model is fascinating because the math accounts for both the expansion of the astronomical unit and the strange behavior of the Moon without requiring any dark matter. The math suggests that the rotation of the star is the missing variable. To visualize this, imagine a spinning top on a smooth floor. As the top spins, the motion creates a tiny vortex in the air around the object. If you place a marble near the spinning top, the marble might be nudged away not by the physical surface of the top, but by the movement of the air itself. Acedo suggested that the rotation of the massive solar mass creates a similar nudge in the fabric of space and time. The model implies that the angular momentum of the Sun is slowly pushing the planets away, a factor that was not included in the original equations of general relativity. Imagine a blueprint for a massive skyscraper. The plan works perfectly for a building that is 10 stories tall, but as the building reaches 100 stories, the blueprint failed to account for the curvature of the Earth. General relativity is the blueprint of the cosmos. The theory works for the orbits that have been measured for centuries, but as the measurements become more precise, the lean in the building becomes visible. The 15-meter expansion is the new Mercury anomaly, a signal that the current master theory is nearing the limit of the model. The third finding is the striking correlation between the solar system expansion and the expansion of the entire universe. Lorenzo Iorio noted in 2011 that the rate of the astronomical unit increase is numerically close to the Hubble constant. The Hubble constant measures the stretching of the fabric of space itself. According to standard physics, the expansion of the universe should not affect the local solar system. The concept is based on the Einstein-Strauss vacuum, the theoretical concept that a gravitationally bound system like this one is isolated from the cosmic stretching of space. The gravity of the Sun is supposed to be strong enough to carve out a pocket of stability, a sanctuary in the expanding sea. However, if the 15-meter drift is real, the sanctuary is not stable. The tension of the entire universe appears to be leaking into the local neighborhood. The correlation suggests that the local physics of the planets is connected to the global fate of the cosmos. The finding implies that the boundaries of local reality are more porous than previously believed. Mankind is witnessing a transition where the local laws are being influenced by the grand scale of the universe. The researchers are standing at a crossroads where one path leads to a local modification of gravity and the other path leads to a universal stretching of space. If the astronomical unit is expanding because of the Hubble constant, then the fundamental laws of gravity must include a cosmological term acting at every scale. This would mean that the expansion of the universe happens right here, in the space between the Earth and the Sun, the same force stretching distant galaxies apart. The paradox of the solar system as a laboratory emerges from the data. Humanity sent probes to the rings of Saturn and mapped the surface of Pluto, yet the movement of the Earth remains a mystery. The paradox is that the solar system is both the most familiar and the most difficult environment to measure. The difficulty arises from the overwhelming complexity of the gravitational environment. The Sun contains 99.8% of the mass of the system, but the remaining fraction of a percent is distributed among 8 planets, hundreds of moons, and millions of asteroids. To find a 15-meter error is like trying to hear a single whisper in the middle of a massive hurricane. Every tiny tug from a distant asteroid or the slight pressure of sunlight must be modeled with total accuracy. The precision of the researchers is staggering. They must account for the relativistic slowing of clocks and the movement of the continents on the Earth. When an anomaly survives this level of scrutiny, the signal is a profound challenge to human understanding. The solar system is a noisy laboratory where the signal of the new physics is buried under a mountain of classical data. The measurement problem is further complicated by the stability of the system over geological time. To understand this paradox, imagine an ancient grandfather clock that has kept time for 300 years. The assumption is that the gears are made of steel and the pendulum is a fixed length. But then, a modern laser measurement reveals that the wooden frame is slowly absorbing moisture and swelling by a few microns every year. The clock still runs, but the fundamental scale of the machine has changed. The solar system is that clock. The planets are the gears, and gravity is the spring, but the entire structure is reacting to an invisible environment. The paradox is that the very stability of the system makes the expansion hard to detect. If the drift were large, the solar system would have fallen apart millions of years ago. The fact that the system is still here means the expansion must be incredibly subtle. The research is looking for the ghost in a machine that is almost perfect. This research pushes the limits of human technology and mathematical patience. The yardstick is failing because the neighborhood is no longer standing still. The closing question of this investigation focuses on the fate of humanity in an expanding system. If the planets are drifting away from the sun, this world is on a slow migration toward the outer dark. The astronomical unit is the primary yardstick of human existence because the distance defines the habitable zone. The zone is the narrow region where the heat from the star allows liquid water to exist on the surface of a planet. If the Earth moves too far, the oceans will freeze and life will end. Lorenzo Edorio investigated this long-term stability in 2010. He found that in 1 million years, the Earth will be 150 kilometers further from the sun. The drift is a study of a slow and inevitable transition. Mankind has treated the solar system as a permanent sanctuary, but the missing meters reveal that the sanctuary is shifting. The realization validates a continued curiosity about the mechanics of the human home. Mankind must keep measuring the pings from the Martian landers and the pulses from the lunar mirrors. The missing meters are an invitation to look closer at the gears of the cosmos. The truth likely lies somewhere between the data and the doubt. This ambiguity is what keeps the world looking at the stars. The investigation into the expansion of the astronomical unit has revealed that the yardstick is more than a tool for measurement. This device records the departure. The solar system is drifting into the dark, and the species is going with the system. Mankind is not the master of gravity, but students who have just discovered that the textbook is missing the final chapter. The yardstick is failing because the laws of the universe are still being written. The investigation into the missing meters has revealed that the neighborhood is not a static clock, but a dynamic voyage. The planet is a fleeting guest in the habitable zone. Mankind has existed with the illusion of an eternal stability, but the drift reveals that the relationship between the Earth and the Sun is evolving. This transformation is the central insight of our journey. The solar system is a changing system, and the expansion of the astronomical unit is the signature of that evolution. The genuine mystery resides in the gap between the observations and the theories. This gap is the space where new science is born. By asking why the solar system is expanding, This investigation is asking about the nature of space and time themselves. The missing meters are a signal that the universe remains a stranger to human mathematics. This investigation ends with the acknowledgement that the cosmic home is a mystery that has only begun to be solved. The truth is written in the missing meters of the yardstick. The planets are drifting, the system is expanding, and the search for the truth continues. The solar system is letting go of the center, and the species is along for the ride. The fascinating part is not that we have answered the question about how incomprehensibly vast the distances in the solar system really are. The reality is that the evidence keeps pointing us towards something bigger and stranger than we expected. Science is not about having all the answers. Science is about asking better questions every time we think we have figured the cosmos out. I hope you found some value in this deep dive into the cosmos. If you enjoyed the content and you want to support the research that goes into these videos, there is a donation link in the description. Your support makes a huge difference and allows me to keep digging deeper into the mysteries of space for all of us. If you know someone who is obsessed with how vast the solar system is, send this video their way. Sharing the video is the best way to help this community grow and reach more curious minds. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.